My favorite question. Let's get this out of the way. Limiting reactant with ideal gas law. If you have 295 milliliters of sulfur dioxide and you react it with 163 milliliters of oxygen, you measure both at a temperature of 315 Kelvin and a pressure of 50 millimeters of mercury. What is the theoretical yield of SO3? So assuming your molar mass is 80.07. So we're looking for our theoretical yield. We can have this in moles and we can have this in grams. So we'll just solve for both for clarity's sake so we know what we're up for. Now, if we're going to react this equation and we have a limited amount of each reactant, we want to figure out which one's the limiting reactant. So we're going to have to get these into moles. So we have to get the amounts here into moles. So we have it in liters and temperature and pressure, but we can figure out how many moles we have by using the PV equals nRT equation. So if we flip this around, we get N, which is our moles, is equal to PV, so pressure times volume, over our R constant times our temperature. So we can do this for both SO2 and O2, and we can figure out how many moles we have. And then after figure out how many moles we have, we look at our ratio to our products and figure out how many moles of our reactant produce how many moles of our product. And then the lowest amount will be our limiting reactant. So let's get started. You have SO2 and we have O2. So let's start off with SO2. So we have N is equal to, then we have our pressure is 50 millimeters of mercury. This is the same thing as torr, and we can just convert this back to atmospheric pressure by dividing by 760 millimeters of mercury. So we say pressure, which is 50 millimeters of mercury over 760 millimeters of mercury. And this gives us our amount in atmospheric pressure. And then we have our volume, which is 295.5 millimeters, so milliliters, I mean. So if we divide by 1,000, it gives us in liters. We have 0.2955 liters, right? And then if we divide all of this, we have our R constant. So I will just write R for now, which that's equal to 0.08206 for atmospheric pressure. And then for temperature, we're going to put 315 Kelvin. So if you solve for this, you get an answer of 7.52 times 10 to the negative 4 moles. Now, if we multiply this by 2 moles of SO3 over 2 moles of SO2, because these are our coefficients, and that gives us our relationship, that's just multiplying by 1. So it's the same answer, 7.52 times 10 to the negative 4 moles of SO3, right? So let's consider O2. So how many moles of O2 do we have, and how many does that produce? So if we do the same thing, 50 over 760, that gives us our atmospheric pressure. Then we have our milliliters here, so we have to change that to liters. So we have 0.1634 liters divided by our R times our temperature, just 315. And this gives us 8.32 times 10 to the negative 4 moles. Now we have to still convert this to how many moles of SO3 do we produce. So we have 2 moles of SO3 produced for every 1 mole of oxygen gas. And so we just have to multiply this number by 2, and that gives us 0.00166. So if I just had to rewrite this, that's 1.66 times 10 to the negative 3 moles of SO3. So that's actually a bigger number than what we have in SO2. So since this is a bigger number, that means SO2 is our limiting reactant. So LR for limiting reactant. So that's how many moles of SO3 we get. So we get 7.52 moles of SO3. So that's, and times 10 to the negative 4. My bad. So if we have that many moles of SO3, that we can stop right there and say this is our theoretical yield. But if we wanted in grams, we just multiply by 80.07, which is our molar mass. And that actually gives us 0.0602 grams. So that's how many grams of SO3 we also have. So those are both our yields or theoretical yields for SO3.